So we'll recap for a minute. What is PFR RTD is a single straight line where tau. What is CSTR RTD is? It is a this kind. So CSTR followed by PFR is this kind of RTD. PFR followed by this CSTR. The RTDs are something like this. They will start at a time of PFR. At what time it will start? Now we will do some more analysis. What happens if PFR and CSTR are in series, parallel? If they are in parallel, let's say VM volume, VP volume, this is let's say V1, this is V2, volumetric flow rate is. Remember, you are injecting here, you are observing here. How does an RTD looks like? So imagine that, let's say you injected, let's say 100 particles here. Depends upon the flow rate, it will go. Let's say 50 is going here, 50 is going here. The 50 which goes here will appear like this, no? Will appear like this. So at the outlet, you will get this kind of RTD. This kind of CSTR RTD. What is area under the curve? How many number of particles? Area under the curve related to, let's say, 50 particles. Now, this 50 at some time, let's say, what is the residence time of PFRE? Let's say consider 5 minutes. What is tau P is? What is tau P is? Let's consider 5 minutes, or let's say 3 minutes. So at 3 minutes time, CSTR gives, let's say, 2 particles, 5, let's say 6 particles. Now, along with this CSTR, along with this 6 are coming from where? CSTR, no? But what is area under the CSTR is corresponds to 50 particles. But at this 3 minutes, you will get exactly 56 particles. So overall 56 particles. So how does the RTD looks like is, you will get this kind of thing. But at, let's say, at tau P, you will get PFR which is merged over the CSTR. These many number of particles are coming from CSTR. On top of this one, you will get the PFR particles. So this will be 50 and area under the curve will be 50. So I'll repeat again. So let's take a CSTR, PFR who are in series. Let's say I injected 100 particles here. 50 goes this side, 50 goes this side. 50 goes here, who goes this side will come like this, no? 50 will come like this, 50 particles. So that will directly, immediately will come here also, no? So they are coming directly here like this. Imagine that there is no PFR. Whatever the 50 goes here will come like this. What is area under this curve is, let's say 50 particles, corresponds to 50 particles. Then the 50 which is going to the PFR has to exit, no? Let's say this is the residence time of tau p. At this tau p, these many number of particles are coming from CSTR, no? Let's say 6 particles are coming. On top of this one, you will get, let's say, this 50 particles, which is 56 particles. So basically, the RTD looks like this. So it is a CSTR, but at one point, you will get whatever the PFR RTD is. Don't give solid line here. This is just the dots I am showing, but it is CSTR particles plus PFR. This E stands for PFR. These many particles stands for CSTR. So PFR particles will be merging on the CSTR. What is 6 is at the time, let's take a CSTR. Let's say initially 15 particles came, later on 14, later on let's say 12, later on 10, later on 6. That 6 is a time, special time. Why I am considering? Because at that time 6 is the particles which are coming from CSTR. What is that residence time is tau p. This 6 will not come at that residence time. You observe suddenly 56 coming. Then you will be surprised. Where is this 56? That 56 is 6 is coming from CSTR because both you are observing here. No, 50 is coming from the PFR. Even I am interested in shape of the RTD, so I am not writing the equations. You have to visualize what is happening in CSTR and PFR. Then only you can draw these RTDs. Suppose if I have, let's say, 2 PFRs in parallel. This is V1, this is V2, VP1, VP2. So what could be the RTD? two vertical lines provided if tau 1 and tau p1 and tau p2 are different. So you will get two vertical lines, let's say tau p1, let's say tau p2. If they are same, then you will get a single straight line. If they are same, you will get a single straight line. It doesn't mean that tau p1 should come first, tau p2 should come later, but it is basically, so depends which one is, let's say if tau p1 is less than tau p2, that is how. If tau p1 is greater than, or let's say tau p2 is smaller, then that is how. What is the RTD if you recycle some of the contents? You have a so what is the RTD? Maybe you will not get directly CSTR, but so I'm asking randomly some of the people. If you have any doubts, something like that, just because I can't ask everybody. If you have any doubts, please let me know. So what happens here is, let's imagine that you send 100 particles. So that 100 particles will go here, 100 particles will come out here, 100 particles will come out there. Now out of 100, let's imagine that 80 particles is going back, then 20 particles will go this way. So first thing is, at residence time of PFR, you will get first your 20 particles. Then what happens next? This 80 particles will come here, 80 particles. 80 particles will come here. Out of 80, 16 will go here, 64 will go here. So when this 16 will come exactly after another residence time, that is 2 tau p. This 16 particles will come. Now this 64 will go, let's say 64 will go here. So 64 will go here. Out of that 64, 20% means something like 13 particles will go here, and then 51 particles will come here. So that 51 will be going like this. Then what is next? 13 particles. At what time? 3 tau p. So you will basically get this kind of small peaks at every. What is difference between these two is tau p. At every time interval, you will get the residence time. Clear? I got already many replies. Good that you are following. So that peaks will continue. So what is residence time of tau p here? How do you calculate tau p? Volume of the PFR divided by volumetric flow rate. What is volumetric flow rate? Let's say V naught. V naught plus R into Vf is what is your tau p, no? Infinity number of peaks, because 80 particles will go, then 20%, like this. This will be continuing. So this is how your tau p calculated. 51 is coming because out of 64, 13 particles goes, then what is left is 51, no? First peak comes at, let's say, tau p. Second peak comes at after tau p, because first peak, like I'll explain one more time. So imagine that you have a CSTR with a recycle. So you injected 100 particles. So these 100 particles, let's say 2 minutes, they will travel to PFR. These 100 particles will travel to PFR of 2 minutes. They will come 100 particles. And out of 100, you are recycling. 20 particles will come here and 80 particles will be recycled back. So basically, after 2 minutes, you will get 20 particles. No, this 80 particles which are coming here will go here. Now they will go to reactor for another 2 minutes. No, so after here you will get 80. Out of 80, 16 will go here and 64 will come here because of recycle. So 16 particles after another 2 minutes. That means 4 minutes resistance time. R equal to 1. If R equal to, then 50 goes this side, 50 goes this side. So like this, multiple peaks come. Yeah, ultimately when it becomes infinity, it becomes zero slowly. Suppose if R, what is tau p? We have calculated. Tau p is V volume of PFR divided by what is volumetric flow rate is V naught into RVF. Suppose if R tends to infinity, then what happens to tau p? Tends to zero, no? That is where the RTD will become, the gap between the straight lines becomes zero. That means you will get a CSTR RTD. So this is PFR with recycle R equal to infinity is nothing but a CSTR. That is what we told. When R becomes infinity, it becomes a CSTR RTD. Yes, first residence time there will be no recycle, but second residence time onwards you will have recycle. So assuming that I have done it in a, imagine that initially also there is some recycle flow. So what we, everybody got it? Any doubts? Just I'm going very slowly here so that you will spend enough time and understand the things. Because why every after recycle particles count is decreasing? Because some of the particles are going to exit, no? It is PFR recycle, no? CSTR doesn't have any recycle. We told that CSTR recycle has no sense. Then we'll consider another concept, which is, let's say, dead time. I just showed some numbers. Out of 80, 20% is 16. Something like that. Don't hung up on, let's say, why it is 16, why not 17. Just some numbers. That time. Suppose if you have a PFR of, let's say, 100 meter cube, and if your volumetric flow rate is 10 meter cube, and then per minute. So you are doing experiment here. Then after experiment, if I see this is how my RTD is. At 5 minutes, I got the peak. This is my experiment. What does this mean? Ideally, where you should get peak? Where you should get peak? 10 minutes, no? But why you are getting peak at 5 minutes? So if you calculate this 5 minutes, when you are getting the peak, that tells you what is the PFR residence time. So what you get is tau P is 5 minutes. So tau P means Vp divided by 10, which is equal to 5. So what is Vp is 50 meter cube. So what it tells is you did experiment on a 50 meter cube PFR only, but your reactor is 100 meter cube. You take 100 meter cube reactor only. This tells you 50 meter cube PFR you did experiments. That means part of the reactor that you have taken is not participating in the reaction. So let's say some of the parts in the reaction, they are not participating. That means these are called as dead zones. They are just volume counting, but no reaction. That means particles are not going there at all. If I inject red plane, that red plane will be traveling like this only, red particles, and exiting. So they are not entering there. So what is that dead zone contributes to 50 meter cube volume? Because this 100 meter cube reactor, your PFR, the volumes which are coming corresponds to peaks, corresponds to actual volumes. Actual volumes. That means you say, I have 100 meter cube volume, but out of 100 meter cube, only 50 meter cube behaves like a PFR. Rest of the 50 meter cube behaves like a dead volume. Clear? So you expect peak here, somewhere here at 10 minutes, you will expect the peak. But your peak is coming at 5 minutes. No, you can't do anything. Then you go back, see where it went wrong is your volume is not true volume. Even though you have 100 meter cube reactor, because there is a possibility of dead zones inside the reactor. So don't get, let's say, Suppose if the red particles which are stuck inside this dead zones, then what happens? Some of the red particles which are stuck inside this dead zones, they will slowly comes out like this. A long tail. This long tail indicates you have dead zones. So particles stuck there and they are coming as it is. Got it? No, when the reactors are old, yes, sometimes it will happen, or let's say there is some catalyst misbehavior or something like that. So dead zones are some corner zones or some zones where there is no mixing at all. Dead zones are possible in CSTR also. Suppose if I have a CSTR, maybe I'll come to CSTR and show it to you. Yes, that long tail will overlap with this one. So this is how the RTD. It is a straight line and a small tail. Long tail kind of thing. That long bleed kind of thing or tail kind of thing is an indication that you have a dead volume, particles stuck there, and they are slowly coming out of the reactor. Yeah, it is kind of not overlapping with the x-axis. It can't overlap now. Little above this, something like that. Yes, if there are more dead zones, then actual volume reduces, residence time reduces. CSTR also there is a possibility. Suppose if I have this CSTR and mixer is like this, then what happens? It mixes only like this, no? If the mixer is not sufficient, then there will be a possibility of dead zone, something like this. How do you identify dead zones here? These are, let's say, some dead zones. Suppose you did experiment on a 100-meter cube reactor and volumetric flow rate is 10 meter cube per minute. Then what is indication in CSTR is the high peak you expected 1 by tau. What is tau m? 100 divided by 10, which is 10. So you expect peak from 1 by 10, no? But actually peak starts from, let's say, 1 by 5. So this is how my RTD. So 1 by 5, it starts peak somewhere here. So that means 1 by tau m is equal to 1 by 5. So tau m is equal to 5. This says Vm is 50. Then you are confused. I did an experiment on a 100-meter cube reactor. No, that means your CSTR has out of this 100-meter cube, 50-meter cube actually CSTR, 50-meter cube is dead volume. So in PFR what happens is peak shifts. In CSTR what happens is peak starts from here. That means highest peak moves in the upward direction. Let's say starting point. Yeah, that means if this is the case, then you should put more stirrers here so that it introduce, you decrease, let's say, dead volume. If you put more stirrers, then what happens is the electricity cost increases. So something like this. So imagine that dead volumes will always be there in most of the reactors. Long tail will not be here, no. So that tail will join with the CSTR. You will not observe this one. Somebody is asking two PFRs in series, two PFRs in parallel have the same graph. How? Two PFRs in series will have a same one peak only, no? Two PFRs in parallel have two peaks. So just take 2 minutes time and go through all the RTDs. We will solve some problems. Just take 2 minutes time. CSTR RTD, PFR RTD, CSTR followed by PFR, PFR followed by CSTR. Then PFRs in parallel. So next one is, what happens if you have a bypass? Suppose if you take a PFR and if you have a bypass. How does this RTD looks? So how does the, what is bypass mean? Suppose if I inject, let's say 100 particles here. Let's say 50 goes this side, 50 goes this side. The 50 which are going here are not spending any time in the reactor, no? So that means if I plot RTD, so you will get first to peak at time t equal to 0 itself. At time t equal to 0, you will get one peak which corresponds to 50 particles. Because this 50 particles, residence time is 0, no? They did not spend any time inside the reactor. Residence time is 0. Then the 50 particles which are going to the reactor will come after, let's say, this much amount of time. So a peak in the initial at time t equal to 0 is an indication of bypass. Indication of bypass in the reactor. If you have a bypass in the reactor, then you will get peak at time t equal to 0 itself. Clear? Bypass in CSTR is not very important. So just if you done, then we will solve one problem. So write this problem. Can I dictate the problem? A pulse of concentrated, so write this problem. A pulse of concentrated KCl solution is introduced as a tracer inside a reaction vessel of volume 1 meter cube. The exit concentration of the tracer a pulse of concentrated KCl solution is introduced as a tracer into the reaction vessel of volume 1 meter cube. The exit concentration of the tracer is given in the picture below. The volumetric flow rate is 1 meter cube per minute. The volumetric flow rate is 1 meter cube per minute. Find a combination of ideal reactors. Which represents the reaction vessel, which represents the reaction vessel. So PFR followed by CSTR. What is the volume of PFR? What is the volume of CSTR? Find last point is find the combination of ideal reactors which represents the reaction vessel. Is there any way to send images in the chat so that I will send particular problem image in the chat? If you have, just Google it out, just let me know, maybe tomorrow. This problem is what is summary of chapter 4. This particular problem is what is summary of chapter 4. This is what is summary. Now somebody will ask a question, why do we need to study the RTD of ideal reactors? Because the reason why we need to study the RTD of ideal reactors is, now look at this, this is a non-ideal reactor now, but if you look at the RTD, what does this RTD suggest? This RTD suggests similar to, let's say, PFR plus CSTR. Immediately look at the RTD. When you look at the RTD, you can say that this is a PFR CSTR RTD. Now, what is the volume of PFR? Take this residence time. 20 seconds is what is, let's say, residence time of PFR. Now, from 20 seconds, if we convert into minutes, tau P is equal to 1/3 minutes. So what is tau P? Vp divided by V, which is equal to 1/3. What is V? 1. So what is Vp? 1/3. Clear? Similarly, right up to this point, Now, what is tau m is also 20 seconds because 1 by tau m is 1 by 20, no? So which is equal to 1 by 3 minutes. What is tau m is Vm by V, which is equal to 1 by 3. What is Vm is 1 by 3 meter cube. Clear? One by 3 meter cube. Now this reaction vessel of 1 meter cube can be represented as PFR of 1 by 3 meter cube plus followed by CSTR of 1 by 3 meter. But you are accounting only 30%, 30%, let's say 66%. No? Then what happens to the rest of 1 by 3? Is nothing but, let's say, dead volume. So this is how you represent the RTD of this one, the RTD of this one, RTD of this one are exactly same. So basically what is this one says is RTD of this is non-ideal reactor and this ideal reactors combination will also have a same RTD, exactly overlapping each other. So RTDs are same. So everybody got it? 20 seconds is 1/3 minute, no? 20 seconds means how many minutes? 1/3, no? Where did we get square? We did not get squares anywhere, no? This is dead volume. See, out of 1 meter cube, 1/3 meter cube is behaving like a PFR, 1/3 meter cube is CSTR. Then what is 1/3 meter cube is dead volume, no? Do you have a model for this one? Suppose when you are starting this experiment. So this is a non-ideal reactor that you take. Now, just solve this problem and hold, understand. I will explain how this problem will be summary of chapter 4. Now go back to your chapter 4 and read the objective. So first class that we have discussed now, what is the objective of chapter 4? Take your notes there, just a minute or 2 minutes, just observe what did we write as a chapter 4, what is the objective. It can be PFR followed by CSTR or CSTR followed by PFR, doesn't matter. So graph is, this graph is RTD of non-ideal reactor or real reactor. This is what is graph. I am not explaining anything. This is what is given now. So basically this RTD are same, no? So what did we started as a chapter 4 objective? So what did we started as a chapter 4 objective? So what did we started as a chapter 4 objective is So what did we started as a chapter 4 objective? Generate what did we started as chapter 4 objective? I don't know, some problem here. Generate, or let's say model for, let's say, I don't know, this board is having some problem. Let's create another board. And what is objective of chapter 4? So what is objective of chapter 4 is, I have a real reactor. You need to generate a model. Or let's say, what is model for this real reactor? This is a real reactor. So how do you generate a model? You have written in our boards. How do you generate a model? First step is find RTD of real reactor. Second thing what we have done now, find a combination of ideal reactors whose RTD is same as RTD of this non-ideal reactor. Clear? Find a combination of ideal reactors whose RTD is same as non-ideal reactor. Now take this question. You have this non-ideal reactor. Let's say you generated this non-ideal reactor of 1 meter cube. No model for this one. Do you have a model? This is the small reactor that you bought from outside, no? Which is equal to, I can write it as simple CSTR followed by PFR followed by dead volume. Do you have model for CSTR, PFR followed by CSTR? Do you have model for PFR followed by CSTR? You have model, no? You know PFR performance equation, you know CSTR performance equation. PFR followed by CSTR, you have a model. This model is nothing but model of this non-ideal reactor. So have you generated model here or not? Whatever the model. So somebody asked me in between one question. When we are starting chapter 4, I don't know who he or she. See, the question is, sir, we are not able to construct ideal PFR or ideal CSTR. Then what is the use of CSTR and PFR? Anyway, you are going to construct a real reactor which is close to PFR or close to CSTR. Clear? So, but you taught in CRE one entire thing, ideal PFR and ideal CSTR equations only. No? When we are not able to construct them, what is the use of PFR, CSTR, and what is the use of their models? The exact use of PFR and CSTR are, they will help you to find a model for a real reactor. They are the tools for finding out the model for a real reactor. Then somebody asked a question, sir, why do we need to study the RTD of ideal reactors? The idea of RTD, or let's say the RTD of ideal reactors, will give you roughly an idea. When you look at the RTD, you can say like, yes, this can be represented as a CSTR PFR in series, or let's say CSTR PFR in, let's say, in parallel, or CSTR, two CSTRs in series, two PFRs in series, or let's say three CSTRs in series, four CSTRs in series, something like that. Clear? That is what is the why we have studied. Did everybody got what is the objective of chapter 4? This is important. This, if you understand whatever we have discussed now, this is what is, it makes your chapter 4 understanding exactly easy. So most of the people will feel here let's say CST or let's say RT or let's say chapter 4 or let's say non-ideal reactor slightly difficult. So I told you, I explained you when we are starting the class itself. CRE, let's say non-ideal reactors is not difficult. It is difficult because of the terminology only. Technically, it is as good as a CRE1. So, did you agree with me? Yes. So now somebody's question I will read. Non-idealities can also mean that CSTR there is no. Yes, yes, yes. The non-idealities means anything which is not behaving like a ideal PFR or ideal CSTR is called as non-ideality. Anything. I want, like, let's take a first order reaction. What is my objective? I should have a ideal PFR. If somebody gives me an ideal PFR, then that is what we are studying. No, that is why, see, somebody is asking, let's say, if why can't we study that reactors only which are, let's say, non-ideal? That is what is chapter 4, no? But then why, suppose if you don't read CSTR and PFR, can you make a model of real reactor? Can you make a model for a real reactor without CSTR and PFR? No, no. Suppose if you don't have the concept of CSTR and PFR, suppose let's say the first problem that we have started in chapter 4 is, I took a first order reaction and PFR volume is 2600, CSTR volume is 4000. Suppose if somebody comes up with a reactor and he says my volume is 3000, how do you say that it is the best? When you compare it, that 3000 with 2600 of PFR, you can say that this is not the best. Whatever you got is, let's say, better reactor, but not the best reactor. Yes, but ideal reactors will give an end, no? So ideal reactors are not there, agreed, I am agreed. But ideal reactors will define the space. What is my extremes? It is always good to know the extremes because you have to play in between the extremes only, no? Clear? So I am going to give, let's say, pause here for 1 or 2 minutes. Just understand, digest, because this is something which you have to digest. That is where I feel most of the people will feel, let's say, chapter 4 is difficult because of the terminology, not because of technical content. I'm going to give, let's say, 1 or 2 minutes. Just solve this problem. I always consider that as a very informative problem because this tells you the objective of a CRE, or let's say what you are going to study in a CRE. So next problem. So I'm not getting any doubts. So somebody is asking to explain what is bypass. I'll explain in the doubts. So dead volumes are something which you can't avoid. By the construction itself, every reactor will have some dead volume. It's not like that I will use every reactor. Like take a distillation column. Why every tray is not behaving like an ideal tray? You can design an ideal tray, no? Can't you design an ideal tray? It is not possible, no? The maximum efficiency that you will get will be 60 or 70%. That is why when you design Maccabee-Thiele diagram, whatever you get is ideal trace. That multiplied by 2 you will get is the non-ideal trace. What is a tray? That is a tray is nothing but where vapor and liquid reaches in equilibrium. That is a single tray. But in reality, that equilibrium reaches in 2 trays. So this non-ideality thing is there throughout the world. Everything is an ideal, non-ideal. Not reactor, not CSTR, not PFR, not heat exchanger. Everything in this world is basically a non-ideal thing. So what you do is you always define what is ideal and you understand how I am deviating from that ideal. Am I 20% close to ideal? Am I 60% close to ideal? Am I 90% close to ideal? Something like this. Even in the students also there is, how do you define an ideal student? Will be different, no? So you deviate from all the students will be, let's say, somebody will be closer to an ideal student. So if I define somebody is an ideal, so then rest of the class will not be same far from the ideal student. No, somebody will be, let's say, very far from an ideal student. Clear? So, right, next problem. A CSTR has a long inlet pipe. A CSTR has a long inlet pipe. A tracer is injected at the entrance of the pipe. A tracer is injected at the entrance of the pipe. The E curve obtained, at the exit of the CSTR is given below. Assuming the plug flow in the inlet pipe, the volume of pipe to volume of CSTR is, assuming the plug flow in the inlet pipe, the ratio of volume of pipe to volume of CSTR is. One is to 4. 1 by 4. It is simple now. What is tau m is 1 by 0.05 because this is 1 by tau m, no? What is tau p is 5. So what is volume of pipe? Pipe volume of CSTR is simply tau p by tau m, which is 5 divided by 1 by 0.05. So which is 0.25 or let's say 1 by 4 because this is tau p. Write this problem. A pulse tracer, a pulse of tracer, a pulse of tracer is injected into the CSTR, is injected into the CSTR of residence time tau. Of residence time tau. The time at which the concentration of the tracer at the exit, the concentration of the tracer at the exit is half of the initial concentration. The concentration at the exit is half of the initial concentration. So 0.693 tau. So what is CSTR? CS into e power minus t by tau. No? When C becomes C naught by 2, C naught into e power minus t by tau. So what is tau is 0.693 tau. So somebody is asking to show the previous question. So write another problem. The curve measured during a pulse tracer experiments. The curve measured during a pulse tracer experiment is shown below. Is shown below. .51. This is concentration versus time. So this is the basically the pulse experiment. These are dots just to indicate. So what is T bar? I think this kind of question we have solved, pulse experiments. Maybe just, this is also a great question. You can take this as a homework and tell me what is the answer maybe, but the answer should be in between 0 to 2. Should you solve this problem? Do you need to solve this problem? Can you tell without solving the problem what could be the answer? Because this is a triangle. What is the area of this entire triangle is half into 2 into 1. So area of the triangle is 1. So E curve and C curve will be same. So this will be same, this will be same. So this is a equal triangle. So this is a great question. Then what is the answer? This area is 0.5, this area is 0.5. Answer will be 1. So you don't, if you solve it by, let's say, you need to translate this into E curve. E curve will be, fortunately, will be same. 1, 0, 2. Then you have to do the integral here, then like that you have to solve. So you don't need to solve. Like that is where actually it helps. When you have fundamentals are right, sometimes you can. So if your fundamentals are good, even if you do a wrong maths, suppose if you get an answer which is out of 2, then your fundamental says answer cannot be beyond 2, no. So that is where it helps. Clear? Even if you solve, you will get the same answer, 1 only. Clear? So yeah, the options will be like I don't know, this is fill in the blanks. No, this is fill in the blanks. So you don't have an option like whatever the answer which are out of 0 to 2, you can out of 0 to 2 you can eliminate. That is not possible here. So I think we will stop it here. More or less we are. So that is where we have done, let's say, one more topic which is remaining in chapter 4 is basically dispersion models, or let's say non-ideal reactor models. So one is dispersion model, tanks in series model, and how do you calculate conversion directly from E curve. So these are some of the models which are remaining. So I think we take one class or 2 classes more. With that one, chapter 4 will be completed. Okay, so we'll stop here and we are open for doubts. Here limits will be 0 to 1 will be one straight line, 1 to 2 will be one straight line. So I'll talk about bypass in the doubts. What is bypass is? So basically, so see, if you have a reactor, it is going like this. Maybe I think tomorrow when I'm explaining, I'll take one session. How do you find, let's say in my plant, my reactor is not working well. How do you diagnose this reactor problems? That is where I'll show you, let's say, how bypass or how, let's say, bypass is simple. Suppose in a packed bed reactor, bypass is simple. In a packed bed reactor, catalyst is something loaded. So because of, let's say, some irregular packing, see the catalyst or let's say flow might be bypassing like this. So entire catalyst is come one side because of some reason, the flow will be bypassed like this. So that bypass means it is not going through the reactor and going out. So in RTDs we have shown it as like this, but in reality what is bypass means it doesn't, it is spends minimum time inside the reactor is what is bypass, because of some malfunction of the reactor. Got it? Bypass means. So somebody is asking me to show the previous page. So is it? So in RTD, it cannot be a single point. No? You are injecting 100 particles. 1 particle will be 1 point. No, 100 particles on a single point. That means it will be a plane. No, what is a plane? Series of points. No, segregation models. Yes, these are there. Dispersion model and tanks in series models are there. So another doubt is in RTD of CSTR PF are combined. So what does the equation 1 by tau equal to? It represents that equation, no? T minus tau, that equation it represents. So you are writing that equation, no? This equation, this is represented. This is represented by that 1 by tau m equal to e power minus t minus tau p by tau m. This is represented by this equation. So till tau p, when you put tau equal to tau p, you will get tau m. That is what is height of the curve. So bypass happens itself because of, let's say, after, let's say, so many years of operation. So there will be some chances of bypass. Bypass doesn't mean that you need to create externally. Sometimes you may need to create externally because of some reason, but sometimes it may happen inside also. So it depends. So when bypass, so basically bypass means something which is going without touching the reactor is called as bypass. Name itself indicates, no? In recycle RTD, the height of the peak decreases after every, because it decreases, no? So first 100 you are sending, out of 120 going. So first 20 will come, next 80 will come. So 20 means 20% of 100. No, next 20% of 80 will be 16. What is left? 64. 20% of 64, which is 13. So then what is left? 51. 20% of 51, something like that. So that is doubts. Somebody asked equation for OD curve. What I don't understand. What is this equation for odd curve? See, in reactors in series, will the pipes used to connect would act as a no, this question is given as PFR is acting as a pipe is acting. But when you are connecting the pipes doesn't act as PFR. There is no temperature and pressure. No. What is reactor? Reactor is nothing but pipe only. Only thing is you are providing temperature and pressure. Bypasses are different. Dead zones are different. They will happen something like that. For dead zone in the reactor topic, you gave the heading dead time. Dead time, dead zone, dead volume, all are same. Basically dead volume. So dead time is also same. Dead time is something that you will get. Is there any other non-idealities? So multiples are there. Non-idealities means something which is not behaving close to ideal. Second moment of RTD means. What does that mean? Second moment of RTD means. What is the meaning? What you are asking, I don't understand. Yes, new added topics will be last. Only one added topic I could see, that is kinetics of enzymatic reactions. Otherwise, I don't see anything else. If two CST are connected in parallel with the same resistance time and different resistance time, graph is same. Which graph? RTD. CSTRs in series will be having a different RTDs. So like when we are discussing tanks in series model, I will tell you what is the RTD of two CSTRs in series. It will not be same. The behavior will be different because when you connect two CSTRs in series, you are moving towards PFR. No, the RTDs will differ. Somebody is asking, there are moments of RTD. I know I'm not understanding your question. Normalized residence time. What you are asking, I am not. Normalized residence time means theta. That is what T by T bar. Maybe I think in tanks in series model I will show you. So basically you calculate, you have E versus T curve, no? Then you find T bar and you plot once again the curve E versus T by T bar, that is called as normalized. I think we'll plot in T by T bar. If you find T bar and if you Divide the x coordinate with t by t bar, that is called as normalized time, theta, that you would call it as E theta curve. So I think no doubt, so I'm closing the session.